Look up at the night sky. What do you see? A scattering of stars, maybe the faint glow of a distant planet. But what if I told you every single one of those pinpricks of light hides a mystery so profound, it bends the rules of reality itself? We're not just talking about distant suns or rocky worlds. We're talking about cosmic wonders, phenomena so strange, so breathtaking, they blur the line between science and magic. Black holes that swallow time, nebulae painting the void with colors no artist could replicate, signals from the depths of space that might, just might, be whispers from another civilization. These aren't just curiosities, they're clues to the universe's greatest secrets, waiting for us to piece them together. This journey isn't about dry facts or textbook explanations. It's about standing at the edge of the unknown and feeling that electric tingle of wonder, the same awe that drove Galileo to point his telescope skyward and Einstein to rewrite the laws of physics. Because here's the truth, the cosmos doesn't play by the rules we've written. It's alive with enigmas that defy logic, challenge our bravest theories, and remind us how much we have yet to learn. And that's what makes it beautiful. So let's dive into 40 of the most mind-bending cosmic wonders ever discovered. Some will leave you questioning reality. Others might send chills down your spine, but all of them will change how you see the universe, not as a cold, empty void, but as a living, breathing puzzle, daring us to solve it. Ready? The cosmos has been waiting. Imagine holding your hand out in front of you, only to realize something invisible is passing right through your fingers. Not ghosts, not magic, but something far stranger, dark matter. This cosmic phantom surrounds us, threads through galaxies, even flows through our bodies every second without us ever noticing. And yet, despite making up over a quarter of the universe, it refuses to show itself. No light, no shadow, no direct trace. So how do we even know it's there? Picture a merry-go-round spinning so fast the children clinging to it should fly off, but they don't. That's exactly what happens with galaxies. The stars at their edges whirl at speeds that defy gravity's rules, as if some unseen hand holds them in place. That hand is dark matter's gravitational pull, the only sign of its presence. Astronomers first caught hints of this in the 1930s, watching galaxies behave as if they were heavier than their visible stars could explain. The math didn't lie, something massive was missing, but here's where the mystery deepens. If dark matter is real, why can't we touch it? Why doesn't it collide with ordinary matter like your desk or your coffee cup? The leading theory suggests it's made of particles unlike anything we've found, particles that ignore light, slip through walls, and barely interact with the universe we know. Scientists have built detectors deep underground, shielded from cosmic noise, waiting for even a whisper of these elusive particles. So far, silence. And then there's the radical alternative. What if dark matter doesn't exist at all? What if instead our understanding of gravity is incomplete? A few daring physicists argue that Einstein's equations might need rewriting, that gravity could work differently on cosmic scales. It's a controversial idea, but that's the beauty of this enigma. It forces us to question the very foundations of physics. One thing's certain, solving the dark matter puzzle could rewrite the story of the cosmos. It shapes how galaxies form, how the universe expands, even how our own cosmic neighborhood will evolve billions of years from now. Whether it's undiscovered particles or a gravitational revolution, the answer won't just satisfy curiosity, it'll redefine reality. So next time you look up at the night sky, remember, the darkness between the stars isn't empty, it's alive with questions. The Milky Way isn't just drifting through space, it's being pulled, as if something colossal has us on an invisible leash. And it's not alone. Thousands of galaxies, including our own, are racing toward a mysterious point in the cosmos at a staggering 14 million miles per hour. Astronomers call it the Great Attractor, and it's one of the universe's most unsettling enigmas. Why? Because we can't even see it, hidden behind thick curtains of dust and stars in our own galaxy's plane. This gravitational monster lurks just 250 million light-years away, cosmically speaking, right next door. It's like hearing whispers from a crowded room but finding the door locked tight. Early observations in the 1970s revealed something bizarre. Galaxies in our local supercluster weren't just moving, they were being funneled toward a single, unseen point. The math pointed to a mass so enormous it could dwarf thousands of Milky Ways. Yet when astronomers looked, they found nothing. At first, scientists thought it might be a supercluster of galaxies, a dense knot of matter with gravity strong enough to tug entire galaxies off course. But when telescopes like the Infrared Astronomical Satellite pierced through the Milky Way's dust, they found only part of the answer. The Great Attractor wasn't the end of the journey, it was a waypoint. Beyond it lies something even larger, the Shapley supercluster, a staggering collection of galaxies so massive, its gravity might be the real culprit behind the pull. But here's where things get weird. Even Shapley's immense gravity doesn't fully explain the Great Attractor's behavior. Some researchers speculate there could be a flaw in our understanding of gravity itself, a cosmic wrinkle that warps space-time in ways Einstein's equations didn't predict. Others wonder if dark matter, that elusive ghost we just discussed, might be clustered there in unfathomable densities, warping the fabric of the universe. What makes the Great Attractor so haunting isn't just its invisibility. It's the reminder of how much we're still blind to. For all our telescopes and probes, the universe keeps its deepest secrets hidden in plain sight. Every answer raises new questions. Is the attractor a destination or just a signpost pointing to something even stranger? One thing's certain, as long as it keeps pulling, we'll keep searching. Now imagine this, a pulse of energy so powerful, it outshines entire galaxies, but only for a millisecond. That's the enigma of fast radio bursts, or FRB. These cosmic flashes erupt without warning, packing more energy than our sun unleashes in 80 years, then vanish as quickly as they appeared. Some burst once and are never heard from again. Others repeat like clockwork, teasing us with patterns we can't yet decipher. And here's the kicker, we still don't know what's causing them. The first FRB was discovered in 2007, buried in old radio telescope data like a whisper in static. Since then, we've caught hundreds more, each one a puzzle wrapped in a mystery. Take FRB 121102, the first repeater ever found. It fires off bursts at irregular intervals, sometimes dozens in a row, then falls silent for months. Then there's FRB 180916, a repeater with a 16-day cycle active for 4 days, quiet for 12, like a cosmic lighthouse on a schedule we don't understand. So what could possibly produce such violent, fleeting signals? The theories range from the plausible to the mind-bending. Colliding neutron stars, dense corpses of dead suns, might create one-off bursts as they smash together. Magnetars neutron stars with magnetic fields so strong they could strip the atoms from your body might crack under the strain, releasing energy quakes that ripple across the universe. But the repeating bursts, those defy easy explanation. Could they be alien megastructures like power beams from civilizations far beyond our own? Even the scientists studying them admit we can't rule it out. Here's what makes FRBs so thrilling. They're not just cosmic curiosities, they're tools. As these bursts race across the universe, they pass through clouds of ionized gas and magnetic fields, leaving faint fingerprints in their signals. By studying those distortions, astronomers have mapped the universe's missing matter, the diffuse gas between galaxies that's nearly invisible to telescopes. FRBs are like flashlights in the cosmic dark, illuminating the structure of everything we can't see. Yet every answer raises new questions. Why do some repeat while others don't? What could possibly power such staggering energy releases? And just if one of these signals ever carries a pattern too precise to be natural, how would we even recognize it? The universe loves a good mystery, and fast radio bursts might just be its most tantalizing yet. One thing's certain: when the next burst arrives, the whole world will be listening. Some stars shine steadily for millions of years, but not Tabby's star. This cosmic oddity, officially named Cancri 8462852, behaves like nothing else in the galaxy. It flickers, it dims. At times, its light drops by a staggering 22%, as if something colossal is passing in front of it, blocking the starlight in ways no natural phenomenon should. And after years of observation, we still don't know why. When astronomer Tabetha Boyajian first spotted this erratic behavior in 2015, the data defied all expectations. Planets too big, dust clouds too irregular. Even Jupiter-sized objects couldn't explain the star's sudden, dramatic dips in brightness. The patterns were so bizarre, some scientists half-jokingly suggested an alien megastructure, a vast swarm of solar panels or habitats built by an advanced civilization to harness the star's energy. The idea wasn't entirely far-fetched. After all, how else could something block that much light without leaving clear traces? But the universe rarely serves up simple answers. Further observations revealed finer clues, hints of dust particles in the star's light, suggesting a more natural, if still mysterious, explanation. Maybe a shattered planet's debris field, or a swarm of comets so vast it dwarfs anything in our solar system, orbits Tabby's star in a slow, chaotic dance. Yet even these theories struggle to explain the full scope of the dimming. The dust doesn't behave as expected, and the timing of the dips remains stubbornly unpredictable. Here's what makes Tabby's star so captivating. It's not just an anomaly, it's a mirror. However this mystery resolves, it forces us to confront how little we truly understand about stars and the strange things that might orbit them. Every time we think we've pinned down the rules, the cosmos throws us a curveball. Maybe it's a natural phenomenon we've never seen before. Maybe it's something we haven't even imagined. One thing's certain: Tabby's star isn't done surprising us. With every new observation, it whispers the same tantalizing question: how many other cosmic secrets are hiding in plain sight, just waiting for us to look closer? Most of the universe is crowded with galaxies, swirling like schools of fish in an endless ocean, except for one terrifying exception. The Boötes Void isn't just empty. It's a cosmic desert so vast, you could fly through it for 330 million light-years and barely stumble upon a single galaxy. To put that in perspective, if our Milky Way were placed inside it, we'd have almost no neighbors for hundreds of millions of years in every direction. And that's precisely what makes it so unsettling. This colossal nothingness, discovered in the 1980s, defies everything we know about how the universe organizes itself. Galaxies cluster together like cities, connected by filaments of dark matter, cosmic highways where matter flows. But the Boötes Void isn't just a quiet street. It's a ghost town spanning 250 million light-years. Only 60 galaxies have been found there when there should be thousands. It's as if someone took a cosmic vacuum and sucked away nearly everything inside. So what could carve out such a void? One theory points to an almost unimaginable event, a collision between universes. Some physicists speculate that our universe might be one bubble in a vast multiverse. and if another bubble brushed against ours in the distant past, it could have left behind a scar of nothingness. Others suggest something even more unnerving. Supermassive black holes, grown to monstrous proportions in the early universe, might have devoured everything in their path, leaving behind this eerie silence. Yet the most plausible explanation might be the simplest and the strangest. The Boötes Void could be a fossil from the Big Bang itself, a pocket of space that never quite filled with matter during the universe's explosive birth. Tiny fluctuations in density left some regions packed with galaxies, while others stretched into emptiness, but even that raises new questions. Why hasn't gravity, over billions of years, pulled galaxies back into this void? Why does it stubbornly resist the universe's tendency to fill every corner with something? What makes the Boötes Void so haunting isn't just its emptiness, it's what it tells us about our place in the cosmos. We assume the universe is uniform, predictable. But this void whispers a different truth, that even on scales we can barely comprehend, the cosmos is capricious, full of surprises that challenge our bravest theories. It's a reminder that for all our maps and models, we're still just beginning to explore the vast, mysterious tapestry of existence. And sometimes the most profound mysteries aren't in the stars, but in the spaces between them. Picture two city-sized spheres spinning toward each other, each packing more mass than our sun, and then, in a fraction of a second, they collide. This isn't science fiction. It's the violent, beautiful reality of neutron star mergers, where the universe's most extreme physics unfolds in a dazzling light show. These dead stars don't just crash, they transform. In their final moments, they forge gold, platinum, and uranium, scattering precious metals across the cosmos like cosmic treasure chests bursting open. Neutron stars are what's left after a massive star explodes in a supernova. Imagine crushing the sun into a sphere the size of Manhattan. The result is so dense, a single teaspoon would weigh 1 billion tons on Earth. Their surfaces are polished smoother than any mirror, their gravity so intense it bends light into bizarre shapes. But when two of these stellar corpses spiral into each other, the real magic begins. The collision unleashes energy equivalent to 1 billion suns, rippling spacetime itself. In 2017, scientists detected gravitational waves from one such merger, tiny vibrations in the fabric of reality, predicted by Einstein a century earlier. But the real surprise came when telescopes swiveled to the spot. There, glowing like an ember, was a kilonova, a fireball of radioactive debris where neutrons ripped apart and reassembled into heavy elements. In seconds, this cosmic furnace produced enough gold to outweigh Earth 100 times over. Here's the twist: nearly all the gold in your jewelry, the platinum in your electronics, even the uranium in some power plants, it likely came from neutron star collisions billions of years ago. These events are the universe's ultimate alchemists, turning the ashes of dead stars into the very elements that make our world possible. Without them, Earth's crust would lack precious metals, and life as we know it might never have sparked into existence. Yet the mysteries don't end there. Some mergers might birth magnetars, neutron stars with magnetic fields so strong they could wipe data from every credit card on Earth from halfway across the galaxy. Others could collapse into black holes, vanishing before our telescopes catch more than a glimpse. And then there's the tantalizing question: could these extreme environments forge elements we've never seen, substances that defy the periodic table? Neutron star collisions remind us that destruction and creation are two sides of the same cosmic coin. In their fiery deaths, they seed the universe with the building blocks of planets, life, even technology. So next time you hold a gold ring, remember, it's not just metal, it's stardust forged in a cataclysm so powerful it echoes across billions of years. The universe teems with possibilities, billions of Earth-like planets orbiting in the so-called Goldilocks zone, where conditions are just right for life. Given the staggering numbers, the math seems undeniable. Alien civilizations should be everywhere. So where is everybody? This is the Fermi Paradox, a question that haunts astronomers and philosophers alike. Named after physicist Enrico Fermi, who famously blurted it out during a casual lunch conversation in 1950, it cuts to the heart of our cosmic loneliness. If life is common, why does the universe feel so empty? One answer is chilling. Maybe civilizations don't last long enough to be noticed. Imagine a species reaching the technological peak, harnessing energy, exploring space, even sending signals only to collapse under war, climate disaster, or runaway artificial intelligence. The universe could be littered with the ruins of civilizations that burned too bright, too fast. It's called the Great Filter Theory, and it suggests that some catastrophic hurdle prevents life from advancing far enough to colonize the stars. The terrifying possibility, we might not have passed it yet, but what if aliens are out there, just nothing like we expect? Silicon-based life forms might thrive in extreme heat or cold, ignoring the planets we consider habitable. Advanced civilizations could communicate in ways we can't detect, using neutrino beams or quantum entanglement instead of radio waves. Or perhaps they've transcended physical form altogether, uploading their consciousness into vast, invisible networks. The universe might be buzzing with life, just not in any shape we recognize. Then there's the zoo hypothesis, the idea that alien societies deliberately avoid us, watching from a distance like scientists observing a nature preserve. Maybe first contact protocols require civilizations to reach a certain maturity before joining the galactic community. Or maybe we're the cosmic equivalent of an uncontacted tribe, left alone until we're ready. But the most haunting answer might be the simplest. What if we truly are alone? What if Earth is a 1 in a trillion fluke, and the silence we hear is exactly what it seems, an empty universe where life is vanishingly rare? It's a humbling thought. Every star, every planet, every galaxy we see might be nothing more than a beautiful, lifeless stage with no audience but us. The Fermi Paradox isn't just about aliens. It's a mirror reflecting our deepest hopes and fears about existence. Whether the answer lies in cosmic catastrophes, unfathomable alien logic, or sheer solitude, one thing's certain: the silence of the universe is the greatest mystery of all. And until we solve it, the question will linger: are we the exception or just the first? They look like cosmic fingers reaching across the void, towering pillars of gas and dust stretching trillions of miles high, silhouetted against a backdrop of newborn stars. The pillars of creation are more than just a breathtaking Hubble image. They're a stellar nursery where suns are born. But here's the twist: by the time you see this, they've already vanished. These iconic structures in the Eagle Nebula, 7,000 light-years away, hold a secret every time we gaze at them. We're looking into the past. The light captured by our telescopes left those pillars when human civilizations were just beginning to rise. And in the millennia since, the universe has rewritten the scene. Shockwaves from nearby supernova have likely shredded these delicate formations, scattering their dust across the nebula like cosmic sandcastles washed away by the tide. What we perceive as solid and eternal is actually a ghost, a fleeting moment frozen in light's slow journey across space. Yet in their destruction lies something extraordinary. The same forces that tore the pillars apart also compressed their gas, triggering the birth of countless new stars. Hubble's infrared vision has peered through the dust, revealing fledgling suns glowing within the pillars like fireflies trapped in amber. Some of these infant stars are still surrounded by disks of material that might one day form planets. Even as the structures fade, their legacy continues, a reminder that in space, death and rebirth are part of the same endless cycle. What makes the pillars of creation truly mesmerizing isn't just their beauty, it's how they force us to confront time's vast scales. Every star field is a mosaic of different eras, a patchwork of moments spanning thousands or millions of years. The universe doesn't pause for us to catch up. By the time we decode one mystery, reality has already moved on. So next time you see that famous Hubble image, remember, you're not just looking at a distant nebula. You're holding a cosmic postcard from a place that no longer exists, sent by a universe that never stops changing. And somewhere in that chaos of collapsing dust and igniting stars, new wonders are already taking shape, ones we won't see for millennia to come. It was just 72 seconds, a blip in the static of the universe, but for those who heard it, those 72 seconds changed everything. On August 15, 1977, a radio telescope at Ohio State University's Big Ear Observatory caught something no one could explain. A signal so powerful, so precise, it seemed to scream artificial. The astronomer who first saw the data circled the printout and scrawled a single word next to it in red ink. Wow! And just like that, the most tantalizing mystery in the search for alien life got its name. The numbers tell part of the story. The signal blasted at a frequency of 1,420 MHz, a quiet channel where cosmic interference is minimal, exactly where scientists had theorized an advanced civilization might broadcast. It was 30 times louder than the background noise, narrow in bandwidth, and matched the profile of a signal coming from deep space. Then, as suddenly as it appeared, it vanished. Decades of searching the same patch of sky near the constellation Sagittarius have never found a repeat. So what was it? The natural explanations all fall short. A passing comet, none were in the area. A satellite or aircraft too slow, and the signal's characteristics don't match human technology of the era. Even a stray reflection off space debris would have left traces elsewhere in the data. The signal's behavior points to something far more intriguing. A burst of radio waves that, for one brief moment, aligned perfectly with what we'd expect from an intentional transmission. But here's the twist. The wow signal wasn't just loud, it was silent in a way that defies natural phenomena. Most cosmic radio sources, like pulsars or quasars, emit across multiple frequencies. This one was laser-focused, as if someone had tuned a transmitter to a single, clear note. And then there's the kicker. The signal's intensity rose and fell over exactly 72 seconds, matching how Earth's rotation would make a fixed celestial source pass through a telescope's field of view. It's as if the universe handed us a perfectly wrapped package labeled, "Examine me," then snatched it away. Could it have been aliens? Even the scientists who discovered it hesitate to say yes, but they can't say no. The signal came from a region without known stars or planets, yet space is vast, and we've barely scratched the surface of what might be out there. If it was a message, it wasn't meant for us. At light speed, the signal would have left its source centuries before humans even invented radio. Maybe it was a cosmic flare gun, an accidental burst from an alien experiment, or a beacon meant for someone else that we just happened to overhear. The wow signal endures because it's the ultimate cosmic teaser, a puzzle with missing pieces. Every few years, a new study claims to crack it, only for the mystery to deepen. Some suggest it was a hydrogen cloud magnified by a passing black hole. Others point to a rogue satellite, long forgotten, but none explain why, after all this time, nothing like it has ever been heard again. Perhaps that's the real lesson here. The universe doesn't owe us answers, it offers fleeting glimpses, whispers in the dark that vanish before we can grasp them. The wow signal might be a fluke, a once-in-a-billion-year coincidence, or it might be proof that we're not listening hard enough, not looking in the right ways. One thing's certain, until another signal comes, that red-inked "wow" on a decades-old printout remains our closest brush with the idea that we might not be the only ones reaching out. And that's enough to keep us listening. We think of planets as orderly worlds, neatly orbiting stars, but the universe loves breaking rules. Meet rogue planets, cosmic nomads untethered to any sun, drifting through the void like ghost ships in the night. Astronomers estimate there could be billions of these free-floating worlds in our galaxy alone, ejected from their star systems by gravitational chaos or born in the cold isolation of interstellar space. And here's the twist: some of them might be hiding secrets that rewrite our definition of habitable. Take CFB-DESA 20149. This rogue, discovered in 2012, isn't just wandering, it's warm. With a surface temperature of around 400 degrees Celsius, it glows faintly from the heat of its formation, a fading ember in the cosmic dark. But colder rogues could harbor something far more intriguing: subsurface oceans. Imagine a planet with a thick, icy shell, its interior warmed not by starlight, but by the slow decay of radioactive elements in its core. Tidal forces from a long-lost moon might churn these hidden seas, keeping them liquid for billions of years. On Earth, we've found life thriving in the most extreme places: volcanic vents, Antarctic ice, even deep underground. Why not in the eternal night of a rogue world? The mechanics are mind-bending. Without a sun, photosynthesis is impossible, but life doesn't always play by Earth's rules. Chemosynthetic organisms could feed on minerals or hydrothermal vents, just as they do in our planet's deepest oceans. Some rogues might even have atmospheres, trapped beneath layers of ice or kept dense by the planet's own gravity, creating pressure cooker environments where exotic biochemistries could unfold. And let's not forget the sheer scale. With so many rogue planets adrift, even a tiny fraction hosting life would mean the galaxy is teeming with it, just not where we've been looking. Detecting these wanderers is like finding needles in a cosmic haystack. They emit almost no light, and their only telltale sign might be a fleeting distortion of starlight as they pass in front of distant stars, a phenomenon called microlensing. But new telescopes, like the upcoming Nancy Grace Roman Space Telescope, are designed to spot these subtle flickers, potentially revealing thousands of rogues we've missed. Every discovery could reshape our understanding of where life might cling to existence. What's most humbling about rogue planets isn't just their strangeness, it's how they expose the arrogance of our assumptions. We hunt for Earth twins around sun-like stars, but the universe whispers, life could be anywhere, even in the freezing dark between the stars. If life does exist on these lone worlds, it would prove that biology is more resilient, more creative than we ever imagined. The cosmos doesn't care what we think is possible. It's out there, right now, writing its own rules, one rogue planet at a time. Imagine tossing a book into a fire. The pages burn, the ink fades, but in theory, if you could track every particle of smoke and ash, you could reconstruct every word. That's the fundamental rule of quantum physics. Information can never truly be lost. But throw that book into a black hole, and the universe's rulebook gets shredded. According to Einstein's relativity, anything crossing a black hole's event horizon vanishes from our universe, crushed into a singularity where space and time break down. So where does the information go? This is the black hole information paradox, a battle between two pillars of physics, and the stakes couldn't be higher. Stephen Hawking kicked off the crisis in the 1970s when he realized black holes aren't completely black. They slowly leak energy, now called Hawking radiation, and over eons they evaporate into nothing. Here's the problem: that radiation appears totally random, carrying no trace of what fell in. If a black hole disappears, taking all information with it, quantum mechanics' most sacred law collapses. Physicists split into warring camps. Some argued information is truly destroyed. Others, like Leonard Susskind, bet their careers it wasn't, leading to one of science's most famous wagers. The breakthrough came from an unexpected place: string theory. In the 1990s, theorists discovered that black holes might store information not in their crushing depths, but on their surfaces. Just like a hologram encodes a 3D image on a 2D film, a black hole's event horizon could hold a scrambled record of everything it swallowed. When Hawking radiation escapes, it might carry tiny imprints of that data, like smoke particles hiding fragments of a burned book's text. But the plot thickens. If information escapes, how? Quantum mechanics demands it can't be copied. Yet relativity insists an infalling observer would see nothing special at the event horizon. This firewall paradox suggests either physics is wrong or black holes are far stranger than we thought. Some theorists propose wormholes threading the radiation back inside. Others suggest reality splits, with information existing both inside and outside the hole, a multiverse in miniature. Why does this matter? Because black holes aren't just cosmic vacuum cleaners. They're laboratories for the universe's deepest laws. Crack this paradox and we might finally unite quantum mechanics and gravity. Fail, and we could be staring at a flaw in reality itself. Every time a black hole swallows a star, it's not just a light show, it's a test. And the universe is waiting to see if we pass. The universe isn't just expanding, it's stretching the limits of what we thought possible. Take the Hercules Corona Borealis Great Wall, a structure so colossal, it makes our local superclusters look like specks of dust. Spanning 10 billion light-years, this galaxy filament isn't just big, it's impossibly big. According to our best models of cosmic evolution, nothing this massive should exist so early in the universe's history. Yet there it is, a thread of galaxies woven across the cosmos like a crack in reality itself. Discovered in 2013 by mapping gamma-ray bursts, the universe's most violent explosions, this great wall isn't something you can see through a telescope. It's a ghostly scaffold traced by the dying screams of massive stars, their bursts clustering in a pattern too precise to be random. Each gamma-ray burst acts like a cosmic flare, marking the location of a galaxy we'd otherwise miss. String enough of them together and a terrifying picture emerges. A structure stretching across a seventh of the observable universe, a web of matter so vast, it defies the cosmological principle, the idea that the universe should look roughly the same no matter where you're standing. Here's where the mystery deepens. The Hercules Corona Borealis Great Wall isn't just large, it's ancient. Light from its galaxies began traveling to us when the universe was barely half its current age. According to our understanding of gravity and cosmic inflation, matter shouldn't have had enough time to clump together on such a mind-boggling scale. It's like finding a skyscraper in the middle of the Stone Age, an artifact that simply shouldn't exist yet. So how did it form? One radical theory suggests the early universe wasn't as uniform as we thought. Tiny fluctuations in density, magnified by inflation, might have created seeds for these cosmic titans to grow faster than expected. Others propose even wilder ideas, like defects in the fabric of spacetime left over from the Big Bang, acting as gravitational anchors for matter. Or perhaps dark matter, that invisible glue holding the cosmos together, clustered in ways we haven't yet imagined, sculpting these walls in the dark. But the most unsettling possibility, this might not be the only one. As our maps of the universe grow more detailed, we're finding other candidate structures like the Sloan Great Wall and the South Pole Wall that push the boundaries of cosmic scale. Each discovery chips away at our assumptions, forcing us to ask, is the universe more uneven, more lumpy than we ever dared to guess? What makes the Hercules Corona Borealis Great Wall so humbling isn't just its size, it's the reminder that for all our theories, the cosmos keeps surprising us. Every time we think we've grasped the rules, the universe throws a curveball, revealing depths we didn't know existed. And that's the beauty of it. The greatest wonders aren't just the ones we can explain, they're the ones that force us to rethink everything. Picture a world where the ground beneath your feet isn't rock, it's diamond, not a few scattered gems, but entire continents of crystallized carbon stretching as far as the eye could see. This isn't science fiction, it's 55 Cancri E, a planet so bizarre it redefines luxury. Twice Earth's size and 8 times its mass, this super-Earth orbits so close to its sun that a year lasts just 18 hours. Surface temperatures soar above 2,000 degrees Celsius, hot enough to melt iron, yet somehow, its core remains a glittering enigma. Astronomers first detected 55 Cancri E in 2004, but its true nature took years to unravel. The key clue, its parent star is unusually rich in carbon. When this planet formed, the sheer pressure in its core millions of times greater than Earth's crushed that carbon into something extraordinary, diamond. Not the delicate gemstones we mine, but a vast planetary-scale lattice of the hardest natural material known. Some estimates suggest a third of the planet's mass could be diamond, a treasure trove worth quadrillions by Earth standards, if anyone could survive long enough to claim it. But here's the twist, this diamond isn't pristine. The surface is likely a hellscape of molten silicon and metallic vapor, where diamond lava might bubble up through cracks in a crust that's more gemstone than geology. The atmosphere, if it exists at all, could be a suffocating mix of hydrogen and helium stripped away by the relentless solar wind and those sparkling continents. They might not even be solid. Under such extreme heat and pressure, diamond could behave like a plastic, flowing in slow, surreal rivers across the planet's surface. What makes 55 Cancri E so fascinating isn't just its composition, it's what it reveals about planetary diversity. We used to assume all rocky worlds would resemble Earth, Mars, or Venus. But this diamond planet proves the universe has a far richer imagination. Carbon-rich systems might birth entire families of such worlds, some with graphite plains or even stranger materials we've yet to discover. And while 55 Cancri E is too hostile for life as we know it, it raises a tantalizing question. Could a colder, more distant carbon planet harbor chemistry we've never dreamed of? Yet the real lesson here is about perspective. From afar, 55 Cancri E sounds like a cosmic crown jewel. Up close, it's a monument to extremes, where the universe takes something precious and places it utterly beyond reach. A reminder that out there, the rules are different and nature's wonders aren't always meant for us. Stretching across the cosmos like a fading bruise, the CMB cold spot isn't just an anomaly, it's a cosmic crime scene. Buried in the afterglow of the Big Bang, this eerie patch of sky glows colder than its surroundings by a fraction of a degree, a subtle clue that belies its staggering implications. Discovered in 2004 by NASA, a Wilkinson microwave anisotropy probe, this frigid expanse spans nearly 200 million light-years, a void so vast it could swallow thousands of Milky Ways. And the most unsettling part, we still don't know what punched this hole in reality. At first glance, the explanation seems simple, a supervoid. These cosmic deserts, regions nearly empty of galaxies and matter, can slightly cool the cosmic microwave background radiation, the faint echo of the universe's birth, as light passing through them loses energy climbing out of the void's gravitational well. But here's the catch, the cold spot is too cold. Even the largest known supervoids can't account for the temperature drop observed. It's like finding a freezer in the middle of a desert. Something far stranger must be at work. That's where the theories get wild. One tantalizing possibility: the cold spot might be a scar from a collision with another universe. In the multiverse hypothesis, our cosmos floats in a vast ocean of bubble universes, each with its own physical laws. If one of these bubbles brushed against ours in the distant past, the energy of that impact could have left behind a cosmic fingerprint, a region of space stretched thin, cooling the radiation that passes through it. It's a radical idea, but the math holds up. Such a collision could precisely explain the cold spot's unusual properties, yet not everyone's convinced. Some astronomers argue the anomaly might stem from a flaw in how we interpret the cosmic microwave background, a kind of optical illusion created by the tangled web of galaxies and dark matter between us and the Big Bang's afterglow. Others propose even more exotic explanations, like a cosmic texture, a crack in spacetime itself, left over from the universe's chaotic infancy. These defects, predicted by quantum field theory but never observed, could warp space in ways that mimic the cold spot's chilling effect. What makes this icy enigma so compelling isn't just the mystery, it's the stakes. If the cold spot is evidence of a multiverse, it would be the first tangible proof that our universe isn't alone. It would mean reality is vaster, stranger, and more interconnected than we ever imagined. But if it's something else, a supervoid, a texture, or even an error in our data, it still forces us to confront how little we understand about the universe's structure. The cold spot lingers like a whisper from the cosmos, a riddle wrapped in the faintest chill of microwave light. Whether it's a doorway to other universes or just a cosmic illusion, one thing's certain: the universe doesn't give up its secrets easily. And that's what makes the hunt so thrilling. Every anomaly, every cold patch in the sky is a challenge, a dare to look deeper, think bigger, and rewrite the story of everything we know. On October 19, 2017, astronomers spotted something that shouldn't have been there: a needle-thin object hurtling past our sun at nearly 200,000 miles per hour. Its trajectory so extreme it could only have come from beyond our solar system. The first known interstellar visitor, later named Oumuamua Hawaiian for Scout, wasn't just passing through. It was breaking every rule we thought we knew about cosmic wanderers. What made Oumuamua so baffling wasn't just its origin, it was how it moved. Unlike comets or asteroids, which follow predictable paths dictated by gravity, this cosmic cigar tumbled end over end, spinning chaotically as if knocked off course by some unseen force. Then came the real shocker. As it raced away from the sun, it accelerated, defying gravity's pull like a car pressing down on the gas. Comets sometimes get a speed boost from evaporating ice, but Oumuamua showed no tail, no gas plume, no visible sign of propulsion. It was as if the universe had tossed a stone into our backyard, only to watch it suddenly change direction mid-air. Scientists scrambled for explanations. Maybe Oumuamua was a shard of nitrogen ice, chipped off a Pluto-like exoplanet. As sunlight vaporized its surface, the escaping gas could have acted like a thruster, nudging it faster without leaving a visible trail. Or perhaps it was a dust bunny of hydrogen ice, so light and porous that solar radiation pushed it like a cosmic sail. But each theory had holes. Nitrogen icebergs should be rare, and hydrogen ice would have evaporated long before reaching us. The lack of a visible coma or tail left researchers grasping at shadows. Then came the wild card. What if Oumuamua wasn't natural at all? Astronomer Avi Loeb famously floated the idea that it might be alien technology, a discarded light sail or derelict probe from another civilization. Its flattened shape, unusual acceleration, and lack of outgassing matched predictions for an artificial object designed to ride starlight. Skeptics dismiss the notion, but Loeb's point stuck. When nature defies expectations, shouldn't we at least consider the extraordinary? The truth is, Oumuamua's greatest legacy isn't in the answers it gave. It's in the questions it forced us to ask. Interstellar visitors might be far more common than we thought, and we've only just built the tools to spot them. Future telescopes like the Vera Rubin Observatory could find dozens more, revealing whether Oumuamua was a fluke or the first glimpse of a hidden population. Until then, this tumbling enigma remains a bookmark in the cosmic mystery novel, a single page torn out, leaving us to wonder what story it belonged to. One thing's certain, the universe doesn't send scouts without a reason. Whether Oumuamua was a frozen relic or something far stranger, its visit reminded us that the cosmos is full of surprises, and we're only beginning to learn how to read them. From a distance, the Sombrero galaxy looks almost too perfect, a celestial jewel suspended against the black velvet of space. Its luminous core bulges like a glowing pearl, encircled by a razor-thin disk of dust so precise it could have been drawn with a cosmic compass. But don't let its serene beauty fool you. This galaxy, catalogued as M104, is a cosmic contradiction, a puzzle wrapped in starlight. Is it a single, flawless spiral? Or the ghostly aftermath of two galaxies colliding, their violent past erased by time? The first clue lies in its structure. Most spiral galaxies like our Milky Way have a modest central bulge, their arms swirling gracefully outward. But the Sombrero's core is monstrous, a dense sphere of ancient stars accounting for nearly a tenth of its mass. This isn't just a bulge, it's the heartbeat of a galaxy that defies classification. Some astronomers argue it's a rare hybrid, a cross between a spiral and an elliptical galaxy. Its disk so thin and its core so dominant that it straddles two cosmic identities. Then there's the dust. That dark, knife-edge ring isn't just decorative, it's a fossil record. Unlike the chaotic dust lanes of younger spirals, the Sombrero's disk is eerily symmetrical, as if smoothed by some unseen hand. One theory suggests this precision is the signature of a long-ago merger, where a smaller galaxy was swallowed whole. The gravitational turmoil would have shredded the victim stars, redistributing them into the Sombrero's swollen core, while the remaining dust settled into that striking equatorial plane. But the plot thickens when you peer closer. Hubble's sharp eye has revealed thousands of globular clusters, dense swarms of stars orbiting the Sombrero. Most galaxies have a few hundred. This one boasts nearly 2,000, more than any other known galaxy its size. Some are ancient, dating back to the universe's infancy. Others are younger, their blue-white glow hinting at more recent births. This imbalance is another smoking gun. Mergers trigger bursts of star formation, leaving behind clusters like breadcrumbs marking a violent feast. Yet the most tantalizing mystery lurks at the galaxy's heart. Hidden within that brilliant core sits a supermassive black hole, one of the largest ever measured, 1 billion times the mass of our Sun. Such behemoths don't grow quietly. They're fed by cataclysms, their gravity gorging on the gas and stars of passing galaxies. The Sombrero's black hole is too big for its galaxy, a cosmic paradox that only makes sense if this serene beauty is actually a predator in repose. What makes the Sombrero galaxy so mesmerizing isn't just its looks, it's the story it whispers across 28 million light-years. Every perfect spiral, every ancient cluster, is a page in a history book we're still learning to read. Whether it's a lone wonder or a merged masterpiece, one thing's clear: the universe's most breathtaking sights often hide the darkest secrets, and sometimes the most elegant answers are written in the scars of chaos. The universe isn't just expanding, it's rushing. Across unimaginable distances, entire clusters of galaxies are being tugged in the same direction at breakneck speeds, as if some cosmic tide is pulling them toward a point beyond the edge of everything we can see. Astronomers call it the dark flow, and it's one of the most unsettling discoveries in modern cosmology. Because if these galaxies are moving toward something outside our observable universe, what or where is pulling them? This eerie motion was first detected in 2008, when scientists studied the peculiar velocities of galaxy clusters, how they deviate from the universe's overall expansion. Using the cosmic microwave background as a reference frame, they found something impossible. Over 1,000 clusters, some billions of light-years apart, were all streaming toward the same patch of sky near the constellations Centaurus and Vela. The kicker, there's nothing there, no supercluster, no immense void, no known structure massive enough to explain the pull. Just empty space, at least as far as our telescopes can see. The numbers defy logic. These clusters are racing at nearly 2 million miles per hour toward nothing, and the scale is staggering. The dark flow extends at least 2.5 billion light-years, possibly farther, meaning whatever's tugging on them lies beyond the observable universe's horizon. That's like standing on a beach, watching every wave roll toward a point past the edge of the ocean. The implications are dizzying. Could this be evidence of another universe, a neighboring bubble in the multiverse, exerting gravitational influence on ours? Skeptics argue it might be a statistical fluke or an artifact of incomplete data. But follow-up studies, including observations from the Planck satellite, only deepen the mystery. The flow persists, its signal too strong to ignore. If it's real, we're staring at a crack in the cosmological principle, the idea that the universe is roughly the same everywhere. Instead, it suggests an asymmetry on the grandest scale imaginable, a cosmic tilt toward something else. What makes the dark flow so haunting isn't just the pull, it's the possibility that we're catching a glimpse of the unseeable. Most of the universe is forever hidden from us, its light too distant to ever reach our telescopes, but gravity doesn't care about light speed limits. It might be the only messenger from realms beyond our cosmic horizon, whispering secrets through the motion of galaxies. Whether it's another universe, a flaw in our understanding of gravity, or something even stranger, one thing's clear: the map of reality just got a lot bigger. And we're only beginning to trace its edges. Most stars fade quietly into the night, but not HD 44179. This aging star, 3,000 light-years away in the constellation Monoceros, is staging one of the cosmos' most dazzling retirement shows. Instead of scattering its gas in chaotic plumes, it's sculpting a masterpiece, the red Rectangle Nebula, a structure so precise, it looks like it was drafted by celestial architects. At first glance, the name fits perfectly. Hubble's images reveal a glowing crimson frame, its sharp angles defying everything we know about how dying stars behave. But zoom in, and the real magic appears: a series of ladder-like rungs stretching from the central star, each step a ripple of ejected gas frozen in time. This isn't just a nebula, it's a cosmic fingerprint, a rare glimpse of order emerging from stellar chaos. The secret lies in the star's unusual dance with itself. Unlike most sun-like stars, which puff off their outer layers in uneven bursts, HD 44179 has a hidden partner, a dense white dwarf orbiting so close it acts like a cosmic chisel. As the dying star sheds material, its companion's gravity shapes the outflow into twin cones of gas, stacking them in precise layers like rings in a tree trunk. Viewed edge-on, these cones create the illusion of a rectangle, their intersecting arcs forming those mesmerizing rungs. But the color, that's another mystery. The nebula's rich red hue comes from an exotic form of carbon molecules, nicknamed red graphene, excited by the star's intense ultraviolet light. These molecules shouldn't survive long in space, yet here they thrive, painting the nebula in shades unseen elsewhere in the universe. Some scientists speculate they're the building blocks of future planets, or even life, scattered like cosmic confetti. What makes the red rectangle so extraordinary isn't just its geometry, it's the fleeting nature of the spectacle. In a few thousand years, the central star will heat up, erasing the delicate structures we see today. The gas will dissipate, the symmetry will unravel, and this cosmic artwork will vanish into the interstellar void. We're catching it mid-performance, a reminder that even in death, the universe creates beauty, not with brushes, but with gravity, light, and time. So next time you gaze at the night sky, remember, not all celestial wonders are grand explosions or swirling galaxies. Some are quiet, meticulous, and achingly transient, like a dying star's final, perfect signature, written in gas and dust. And in that signature, we find the universe's most startling truth. Even in endings, there's artistry beyond our wildest imagination. The Andromeda galaxy looks peaceful from afar, a swirling pinwheel of stars floating in the void. But don't let its serene glow fool you. This cosmic neighbor is a predator and its latest meal. A dwarf galaxy called M32, currently being torn apart strand by strand, its stars sucked into Andromeda's gravitational maw like cosmic spaghetti. This isn't some rare event, it's standard behavior for a galaxy like Andromeda, a celestial titan that's grown to its enormous size by devouring smaller neighbors. And in 4 billion years, it's coming for us. The evidence of Andromeda's feasting is written in the stars. Streams of orphaned suns, stellar debris from past collisions stretch across the galaxy's outer halo, tracing the remnants of meals consumed over billions of years. Some of these streams are still fresh, their stars not yet fully assimilated into Andromeda's structure. Others are so ancient, their origins are nearly erased, absorbed so thoroughly they're now indistinguishable from Andromeda's native stars. Astronomers call this galactic cannibalism, a slow-motion process where large galaxies grow even larger by consuming smaller ones, and Andromeda is one of the most voracious eaters in our cosmic neighborhood. What makes this even more unsettling is the inevitability of our own fate. The Milky Way and Andromeda are hurtling toward each other at 250,000 miles per hour, locked in a gravitational dance that will end in a head-on collision. When they finally meet, it won't be a fiery explosion. Stars are so far apart that direct impacts are rare. Instead, it'll be a drawn-out merger, a billion-year tango where gravity reshapes both galaxies into something entirely new. The Milky Way's spiral arms will warp and twist, its stars flung into chaotic new orbits. Andromeda's neat disk will ripple with tidal forces, its core merging with ours into a single, monstrous black hole. But here's the twist: this cosmic feast isn't just destruction, it's creation. Galactic collisions trigger bursts of star formation, igniting nurseries of new suns from the compressed gas of merging galaxies. The resulting hybrid, dubbed Milkdromeda by astronomers, might look nothing like its parents, evolving into a featureless elliptical galaxy over time. Earth, if it still exists, will witness skies filled with strange new constellations, the familiar Milky Way erased by the chaos of merger. What makes Andromeda's predation so mesmerizing isn't just the scale, it's the timescale. Human history is a blink compared to the slow, inevitable grind of galactic evolution. We're watching a single frame of a movie that's been playing for billions of years. And yet, in that frame, we've decoded enough to see the ending. The universe doesn't rush, it feasts slowly, savoring every bite. and in the end, even giants like the Milky Way are just part of the menu. Stars aren't supposed to come back from the dead, but the universe loves breaking its own rules. Meet the zombie stars, white dwarfs that refuse to stay dead, clawing their way back into existence in violent, explosive rebirths. These cosmic phoenixes should have faded into cold, dark embers after exhausting their nuclear fuel. Instead, they stage the ultimate cosmic comeback, stealing matter from neighboring stars like celestial vampires until they reach a critical mass, and then boom. They detonate in thermonuclear fury, outshining entire galaxies in their second act. Take the case of Tycho's supernova, a star that blazed to life in 1572, shocking astronomers who thought the heavens were unchanging. Centuries later, we've pieced together what happened. A white dwarf, the dense corpse of a sun-like star, siphoned gas from a companion until it crossed the Chandrasekhar limit, about 1.4 times the mass of our sun. At that threshold, the pressure in its core reignited runaway fusion, triggering a Type Ia supernova so bright it was visible to the naked eye for months. But here's the twist. Unlike the explosive deaths of massive stars, which leave behind black holes or neutron stars, these standard candle supernova obliterate the white dwarf completely. No corpse, no remnant, just a glittering shockwave of heavy elements blasted into the cosmos. Yet even among these stellar revenants, some defy expectations. Consider the Super Chandrasekhar zombies, white dwarfs that somehow surpass the theoretical mass limit without immediately exploding. One theory suggests rapid spin could stabilize them, their centrifugal force counteracting gravity's crush. Others propose these overachievers might be the product of two white dwarfs merging, their combined mass tipping the scales unpredictably. Then there's the real oddballs like LP40-145, a white dwarf caught in the act of cannibalizing its companion, its surface littered with the spectral fingerprints of stolen material, oxygen, neon, even traces of silicon. It's a slow-motion heist with the thief growing heavier by the day, inching toward its inevitable explosion. What makes these undead stars so fascinating isn't just their violence, it's their role as cosmic alchemists. Every Type Ia supernova seeds the universe with iron, nickel, and other heavy elements essential for planets and life. Without these stellar resurrections, the periodic table would be barren, and Earth might never have formed. But the deeper mystery lies in their uniformity. Because they ignite at nearly identical masses, these supernovae burn with predictable brightness, serving as mile markers for measuring the universe's expansion. It's why they led to the discovery of dark energy. A zombie star's death helped reveal the force accelerating the cosmos itself. Yet for all we've learned, zombie stars keep surprising us. In 2014, astronomers spotted a supernova that flickered multiple times before its final detonation, a white dwarf that seemingly tried and failed to die, like a candle sputtering back to life. Others explode prematurely, their flames fizzling into peculiar IAX supernova that leave half-dead remnants behind. Each anomaly forces us to rewrite the stellar rulebook, proving that even in death, stars have more tricks up their sleeves. So next time you gaze at the night sky, remember, some of those tranquil pinpricks of light are ticking time bombs, biding their time until they steal enough life to blaze brighter than a billion suns. The universe doesn't just let stars die quietly. Sometimes it lets them cheat death and rewrite the cosmos in the process. Galaxies should be bright, bustling cities of stars, but the universe has other ideas. Floating like ghostly mirages in the cosmic dark, ultra-diffuse galaxies defy every expectation. Take Dragonfly 44, a cosmic paradox so faint it was overlooked for decades. This wispy smudge in the Coma cluster contains barely 1% the stars of our Milky Way, yet somehow weighs just as much. The secret, a skeleton of dark matter so dense, it makes these ethereal islands 99.99% invisible. They shouldn't exist, and yet there they are, silent, sprawling, and rewriting the rules of galactic evolution. The discovery of Dragonfly 44 in 2016 sent shockwaves through astronomy. Most galaxies follow a simple formula. More stars mean more gravity, which pulls in more gas to form even more stars. But ultra-diffuse galaxies break this cycle entirely. Their star-forming gas was stripped away eons ago, leaving behind a handful of ancient suns adrift in a sea of unseen mass. Without dark matter's gravitational glue, these fragile structures should have disintegrated long ago, torn apart by the gravitational tides of their galaxy clusters. Instead, they persist like cosmic jellyfish, delicate, tenacious, and utterly mysterious. What makes these galaxies so bewildering isn't just their darkness, it's their defiance of scale. Some, like Dragonfly 44, stretch as wide as the Milky Way but glow with only 1/200th the starlight. Others, like the recently discovered dark free-floating galaxies, drift alone in the void without any dark matter at all, appending the assumption that it's essential for galactic survival. It's as if the universe is running multiple contradictory experiments in galaxy formation, and we've stumbled into the lab mid-trial. Theories scramble to explain them. Maybe they're the stripped cores of once normal galaxies, their outer layers shorn off by violent collisions, or perhaps they formed in pockets where dark matter clustered unusually thick, like butter swirled unevenly through cosmic batter. Some simulations even suggest they could be failed galaxies, regions where gas never quite condensed enough to ignite star formation, leaving behind ghostly outlines of what might have been. Yet the most tantalizing possibility is that ultra-diffuse galaxies are the missing link in the dark matter puzzle. Their extreme ratios of dark to visible matter make them perfect laboratories for testing whether dark matter behaves as predicted, or if our models need a radical overhaul. Already, Dragonfly 44's sluggish star motions hint that dark matter might be fluffier than expected, its particles interacting less frequently than standard theories assume. These phantom galaxies remind us that the universe thrives on paradox. For every blazing quasar, there's a shadowy counterpart whispering secrets we're only beginning to hear. And sometimes the most profound truths hide not in the light but in the delicate, almost not, their glow of the nearly invisible. Some stars burn bright and die young, but HD 140283, nicknamed the Methuselah star, is the cosmic equivalent of a living fossil. This ancient sun, drifting through the constellation Libra, holds a record that once shook astronomy to its core, an age estimate of 14.5 billion years. That's older than the universe itself. When scientists first calculated Methuselah's age in the early 2000s, the numbers didn't just raise eyebrows, they sparked a crisis. The universe, as measured by the cosmic microwave background, is only 13.8 billion years old. How could a star predate the cosmos that birthed it? For a while, astronomers grappled with the unthinkable. Either their stellar dating techniques were catastrophically wrong, or the Big Bang wasn't the beginning we thought it was. The key to the mystery lay in Methuselah's unusual composition. This star is a relic from the universe's infancy, part of the rare population 2 group, stars born before heavy elements like iron were common. Its atmosphere is almost pure hydrogen and helium, with barely a trace of metals. Initially, astronomers used this metal-poor signature to estimate its age, but they hit a snag. Without heavier elements to act as cosmic coolant in its early stages, Methuselah's core would have burned slower, extending its lifespan beyond expectations. Revised models in 2013 incorporating better measurements of the star's distance and brightness, adjusted its age downward to around 14.4 billion years, still staggeringly old, but now with enough wiggle room to fit within the universe's timeline. The margin of error, a comfortable billion years, crisis averted mostly, yet Methuselah's story isn't just about numbers. This star is a time capsule carrying the chemistry of the cosmos's first stellar generation. Its light whispers secrets from an era when galaxies were just beginning to coalesce, when the universe was a darker, simpler place. Unlike younger stars, which are polluted by the remnants of dead predecessors, Methuselah's pristine makeup offers a snapshot of primordial space, untouched by the recycling of supernova. What makes this celestial elder so captivating isn't just its age, it's the reminder that our cosmic clocks are still being fine-tuned. Every observation, every recalibration, peels back another layer of the universe's history. Methuselah's star doesn't just defy time, it teaches us how much we still have to learn about measuring it, and somewhere in its ancient glow, there might be clues waiting to rewrite the next chapter of cosmology. Saturn's North Pole shouldn't exist, at least not the way we see it. While most planets spin their storms into swirling ovals or chaotic spirals, Saturn has sculpted something geometrically impossible. A perfect hexagon, 20,000 miles wide, with sides longer than Earth's diameter. This six-sided maelstrom has raged for decades, perhaps centuries, its razor-sharp edges defying every law of fluid dynamics we know. Hurricanes on Earth dissolve into ragged curves within days. Jupiter's great red spot, for all its fury, is just a blurry ellipse, but Saturn's hexagon, it's as if the planet hired a cosmic architect. The first hints of this anomaly came from Voyager's grainy images in the 1980s, dismissed by some as camera artifacts. But when Cassini arrived in 2004, the truth was undeniable. There it was, a honeycomb of jet streams spinning at 220 miles per hour, each side a near-perfect straight line stretching 13,800 kilometers. The structure isn't just skin-deep, it towers hundreds of kilometers vertically, a towering prism of wind with no known parallel in the solar system. Physicists have thrown every model at this enigma. On Earth, fluid systems sometimes form temporary polygons in lab experiments, but only under carefully controlled conditions, never at planetary scales, never with such precision. One theory suggests resonance is key. Deep beneath Saturn's clouds, layers of rotating gas might interact like gears, their rhythmic motions stabilizing the hexagon's shape. Others point to beta drift, a phenomenon where swirling fluids on a spinning sphere can self-organize into geometric patterns, but no simulation fully replicates the hexagon's crisp edges or eerie longevity. Then there's the wild card. Saturn's hexagon isn't static. Infrared scans reveal it pulsates, shifting colors with the seasons as sunlight dances across its cloud tops. During the planet's long winter, the vortex churns beneath a hazy stratosphere, only to re-emerge decades later, unchanged when spring arrives. It's as if the hexagon exists outside time, a celestial monument to forces we can't yet fathom. What makes this structure so mesmerizing isn't just its defiance of physics, it's the lingering question of what else might be hiding in plain sight. If Saturn can carve a perfect hexagon into its atmosphere, what other unseen rules govern planetary weather? Could gas giants light years away harbor even stranger storms, their geometries limited only by our imagination? For now, the hexagon remains a silent sentinel at Saturn's pole, a reminder that even in our own backyard, the universe still holds blueprints we're only beginning to trace. The moon hangs in our sky like a silent sentinel, gray, pockmarked, and seemingly frozen in time. But pick up a lunar rock and it whispers a different story. Locked inside these ancient fragments is a secret that defies everything we thought we knew about our nearest celestial neighbor. The moon once had a magnetic field. Not just a faint flicker, but a protective shield rivaling Earth's at its peak. This revelation turns the moon from a dead relic into a world that once thrummed with hidden energy, its core churning with forces we're only beginning to understand. How could a world so small, just 1% of Earth's mass, generate such a magnetic dynamo? On Earth, our field comes from a molten outer core of iron and nickel, swirling like a cosmic whirlpool as the planet rotates. But the moon, it's long been assumed too tiny, too cold to sustain that kind of internal fire. Yet Apollo mission samples from the 1970s told a different tale. Tiny mineral grains in lunar basalt were found magnetized, their atomic structures frozen in time like compass needles, pointing to an era when the moon was alive with magnetic storms. The leading theory is as elegant as it is surprising. The moon's core wasn't always the cold, solid lump we imagine today. Billions of years ago, it may have been molten, heated by the lingering energy of its violent birth when a Mars-sized object slammed into Earth, hurling debris into orbit that coalesced into our moon. That primordial heat, combined with tidal forces from a much closer Earth, could have kept the core liquid and turbulent long enough to spin up a magnetic field. Some models even suggest the moon's mantle might have acted like a giant battery, its slow convection generating electrical currents that amplified the field. But here's the twist: that magnetic shield didn't last. By around 1 billion years after its formation, the moon's core began to cool and solidify, its dynamo sputtering out like a dying engine. The field collapsed, leaving the lunar surface exposed to the full fury of solar winds and cosmic rays, which is why today the moon is a barren wasteland of radiation-baked dust. Without that protective shield, any atmosphere it might have had was stripped away, and water molecules at its poles became the only survivors, trapped in eternal shadows. What makes this magnetic mystery so captivating isn't just the moon's past, it's what it reveals about other worlds. If something as small as the moon could briefly mimic Earth's dynamo, what does that mean for exoplanets we've dismissed as too tiny to be habitable? Could some of them, against all odds, harbor magnetic shields protecting alien atmospheres? The moon's hidden history forces us to rethink the boundaries of planetary potential. So next time you gaze up at that familiar gray disk, remember, it wasn't always so quiet. Beneath those cratered plains lies the ghost of a molten heart, a reminder that even the most lifeless-looking worlds can have stories of fire and motion buried in their bones. And somewhere in those rocks, there might still be clues waiting to rewrite the next chapter of the moon's forgotten dynamo. The universe teems with possibilities, billions of Earth-like planets orbiting in the so-called Goldilocks zone, where conditions are just right for life. Given the staggering numbers, the math seems undeniable. Alien civilizations should be everywhere. So where is everybody? This is the Fermi Paradox, a question that haunts astronomers and philosophers alike. Named after physicist Enrico Fermi, who famously blurted it out during a casual lunch conversation in 1950, it cuts to the heart of our cosmic loneliness. If life is common, why does the universe feel so empty? One answer is chilling. Maybe civilizations don't last long enough to be noticed. Imagine a species reaching the technological peak, harnessing energy, exploring space, even sending signals only to collapse under war, climate disaster, or runaway artificial intelligence. The universe could be littered with the ruins of civilizations that burn too bright, too fast. It's called the Great Filter Theory, and it suggests that some catastrophic hurdle prevents life from advancing far enough to colonize the stars. The terrifying possibility, we might not have passed it yet, but what if aliens are out there just nothing like we expect? Silicon-based life forms might thrive in extreme heat or cold, ignoring the planets we consider habitable. Advanced civilizations could communicate in ways we can't detect, using neutrino beams or quantum entanglement instead of radio waves. Or perhaps they've transcended physical form altogether, uploading their consciousness into vast, invisible networks. The universe might be buzzing with life, just not in any shape we recognize. Then there's the zoo hypothesis, the idea that alien societies deliberately avoid us, watching from a distance like scientists observing a nature preserve. Maybe first contact protocols require civilizations to reach a certain maturity before joining the galactic community. Or maybe we're the cosmic equivalent of an uncontacted tribe, left alone until we're ready. But the most haunting answer might be the simplest. What if we truly are alone? What if Earth is a 1 in a trillion fluke, and the silence we hear is exactly what it seems? An empty universe where life is vanishingly rare. It's a humbling thought. Every star, every planet, every galaxy we see might be nothing more than a beautiful, lifeless stage with no audience but us. The Fermi Paradox isn't just about aliens. It's a mirror reflecting our deepest hopes and fears about existence. Whether the answer lies in cosmic catastrophes, unfathomable alien logic, or sheer solitude, one thing's certain: the silence of the universe is the greatest mystery of all. And until we solve it, the question will linger: are we the exception or just the first? Galaxies usually follow a script: spirals with elegant arms, ellipticals like fuzzy blobs, or messy irregulars shaped by collisions. Then there's Hoag's object, a cosmic pulse, so flawless it looks photoshopped, floating 300 million light-years away in Serpens. This ring galaxy is a perfect circle of young blue stars orbiting an ancient golden core, with nothing but eerie blackness between them. No bars, no spiral trails, no signs of a violent past, just a halo of starlight so precise it defies every textbook on galactic evolution. When astronomer Arthur Hoag stumbled upon this anomaly in 1950, he initially thought it was a visual trick, perhaps a gravitational lens bending light into a ring. But decades of scrutiny have only deepened the mystery. The core and the ring rotate at different speeds, yet the structure remains impossibly balanced, like a celestial carousel frozen mid-spin. Most ring galaxies, like the famous cartwheel, form when smaller galaxies punch through larger ones, sending shockwaves that trigger star formation in a circular ripple. But Hoag's object shows no scars, no debris, no sign of a perpetrator. It's as if it was born this way, a cosmic rarity that skipped the chaos of its peers. Theories scramble to explain its isolation. One camp argues it's the aftermath of a near-miss collision billions of years ago, where a passing galaxy's gravity stretched the victim's outer layers into a ring without ever touching the core, like a stone skipping over a pond, leaving perfect ripples but never sinking. Others propose an even rarer scenario, a quenched galaxy that ran out of gas early, its core aging while a late influx of intergalactic material ignited star formation only in the outskirts. Then there's the wild card: what if this is a failed barred spiral? Most galaxies develop central bars that funnel gas outward, but Hoag's object might represent a stalled version. Its bar dissolved before it could sculpt spiral arms, leaving behind this minimalist masterpiece. What makes Hoag's object so mesmerizing isn't just its beauty, it's the questions it whispers about galactic diversity. For all our catalogs of billions of galaxies, we've found fewer than 20 true ring galaxies like this one. Each is a cosmic rebel, a reminder that the universe doesn't always play by the rules. and in their defiance, they hint at hidden chapters in the story of how galaxies grow, evolve, and sometimes, just sometimes, achieve perfection against all odds. Deep within the heart of our galaxy, something stirs a sleeping giant that doesn't just shape the stars around it, but might reach across 26,000 light-years to touch life on Earth. The Milky Way's core isn't just a dense cluster of stars orbiting a supermassive black hole. It's a cosmic lighthouse periodically firing beams of high-energy radiation so powerful they ripple through the entire galaxy. These are galactic superwaves, and their fingerprints might be etched into Earth's fossil record in the most unexpected way: mass extinctions. The theory begins with an anomaly in the ice. Deep Antarctic cores reveal layers rich in radioactive isotopes like iron-60 and beryllium-10, elements that shouldn't exist naturally on Earth. Their origin: cosmic rays, likely from a nearby supernova or something even more exotic. A surge of energy from Sagittarius A, our galaxy's central black hole. When astronomers traced these isotopes to specific time periods, a chilling pattern emerged. Peaks in radioactivity align eerily with extinction events, including the die-off that wiped out nearly 90% of marine species 260 million years ago. But how could something so distant affect us? Picture the galactic center as a pressure cooker. As matter spirals into Sagittarius A, it doesn't always fall smoothly. Sometimes the black hole's magnetic fields twist into knots, snapping like rubber bands and launching jets of radiation outward. These outbursts, lasting centuries or millennia, would flood the galaxy with cosmic rays, stripping atmospheres, mutating DNA, and potentially triggering climatic chaos. Earth, floating in the galactic suburbs, wouldn't be spared. Superwaves could punch holes in our magnetosphere, allowing radiation to rain down and destabilize ecosystems. The evidence isn't just in the ice. Tree rings from ancient bristlecone pines show unexplained growth surges around 12,000 years ago, coinciding with the Younger Dryas event, a sudden plunge into an ice age that wiped out mammoths and other megafauna. Sediment layers from that period contain nanodiamonds and soot, hints of continent-scale wildfires. Could a galactic superwave have triggered this catastrophe? Some researchers argue these cosmic pulses might also explain bizarre mutations in fossil records, sudden leaps in evolution when radiation scrambled the genetic playbook. Yet skeptics counter that the timing is too loose, the evidence too circumstantial. After all, extinction events have many culprits: volcanoes, asteroids, even slow changes in ocean chemistry. But here's what's undeniable: our galaxy isn't the static backdrop we once imagined. It's a dynamic, sometimes violent place, and Earth is adrift in its tides. Whether superwaves are the hidden hand behind life's greatest die-offs or just one player in a complex cosmic drama, they force us to confront a humbling truth. The story of life on Earth might not be written solely by local forces, but by whispers from the heart of the Milky Way itself. Most spiral galaxies announce themselves with bold, star-studded arms, but not the Phantom Galaxy. Drifting 25 million light-years away in Pisces, Messier 74 is a celestial specter, its delicate spiral structure so faint it nearly vanishes against the cosmic dark. This grand design spiral, a classification reserved for galaxies with near-perfect symmetry, should be a masterpiece of cosmic architecture. Instead, its arms are mere wisps of starlight, so ethereal they challenge our very definition of what a galaxy can be. What makes the Phantom Galaxy so mesmerizing isn't just its ghostly appearance, it's the mystery of its missing mass. Typically, galaxies this well-structured are packed with gas and dust, their spiral arms glowing with newborn stars. But M74 is starving. observations reveal it contains just a fraction of the hydrogen expected for its size, as if some unseen hand has siphoned away its stellar fuel. One theory points to gravitational theft. A close encounter with neighboring galaxies might have stripped its gas, leaving behind this skeletal beauty. Another possibility is even stranger, that M74 formed in a void, a pocket of the universe where raw materials were always scarce, forcing it to build its grandeur from cosmic scraps. Yet against all odds, the phantom galaxy clings to its symmetry. Its arms unwind in a flawless logarithmic spiral, each curve mathematically precise despite the lack of dense star-forming regions. This delicate balance hints at hidden forces at work, perhaps a dark matter halo, invisible but massive, that stabilizes its fragile structure. Or maybe its very faintness preserves its perfection. Without the turbulence of rampant star formation, M74's spiral pattern remains undisturbed, like a ripple frozen in a cosmic pond. The real magic happens when we peer beyond the visible. Ultraviolet telescopes reveal what our eyes can't see, bursts of star formation flickering along those faint arms like distant lighthouses. These young, hot stars, massive and short-lived, paint the galaxy in wavelengths invisible to human eyes, proving that even ghosts can harbor sparks of creation. Meanwhile, radio telescopes detect whispers of hydrogen gas threading through the darkness, a fragile web that might one day ignite new stellar nurseries. What makes M74 so humbling is its defiance of expectations. In a universe where bigger and brighter often dominate, this whisper of a galaxy reminds us that beauty thrives in subtlety. Its existence challenges astronomers to rethink how galaxies evolve on the fringes of emptiness, where resources are thin but elegance persists. And perhaps most remarkably, it serves as a cosmic metaphor, proof that even in the darkest corners of existence, structure and symmetry can emerge, fragile but unbroken. Black holes are the universe's ultimate anchors, cosmic sinkholes so heavy, not even light can escape their grip. So when astronomers spotted one streaking through intergalactic space at 5 million miles per hour, dragging a comet-like tail of newborn stars behind it, it wasn't just surprising. It was downright impossible. This rogue behemoth, weighing as much as 20 million suns, had been violently ejected from its home galaxy, leaving astronomers scrambling to answer one question. What kind of cosmic catastrophe could kick a supermassive black hole into the void? The discovery began with a streak of blue. Hubble images revealed an eerie line of young, blazing stars stretching 200,000 light-years, twice the width of our Milky Way, with no galaxy at its head. At the tip of this stellar contrail, a brilliant, compact object blazing with the telltale glow of a supermassive black hole's accretion disk. Somehow, this monster was plowing through the thin gas between galaxies, compressing it into dense knots that ignited into stars in its wake. It was like finding a lone locomotive racing across open country, spewing a trail of fireflowers behind it. The leading theory is as dramatic as the sight itself, a galactic showdown. When two galaxies merge, their central black holes eventually spiral together, locked in a gravitational dance. If a third black hole enters the fray, perhaps from a previously absorbed dwarf galaxy, the trio can engage in a chaotic gravitational tug of war. The lightest black hole gets flung outward like a slingshot pellet, while the remaining two recoil in the opposite direction. But in rare cases, the math gets wilder. If all three black holes interact just right, one can be ejected at unimaginable speeds, carrying the energy of 1,000 supernova. That's likely what happened here. A black hole catapulted so hard, it escaped its galaxy's gravity entirely. Yet the real marvel isn't just the black hole's exile, it's the stellar trail it leaves behind. As the black hole barrels through intergalactic space, its immense gravity pulls gas into a shockwave ahead of it, like a cosmic plow piling up snow. Behind it, this gas collapses under its own weight, igniting into young, blue stars. These aren't just any stars, they're orphans, born far from the nurturing arms of any galaxy, their existence defying conventional star-forming wisdom. Normally, stars need the dense, turbulent clouds found within galaxies to form. But this runaway black hole is rewriting the rules, proving that even in the desolate voids between galaxies, nature finds a way to create. What makes this rogue so mesmerizing isn't just its violence, it's the lingering questions. How many more of these cosmic fugitives are out there, invisible because they're not actively feeding or trailing stars? Could their high-speed journeys seed the universe with rogue stars, planets, or even life in the most unexpected places? And most hauntingly, could this happen to the black hole at the heart of our own Milky Way one day? For now, this celestial outlaw serves as a reminder. The universe doesn't play by our rules. It's chaotic, unpredictable, and far more creative than we dare imagine. Even the mightiest forces, black holes that shape entire galaxies, can become cosmic nomads, painting the void with starlight as they flee the only homes they've ever known. Imagine a world where the skies don't rain water, they rain jewels. Not metaphorically, not poetically, but literally. HAT P7b, a scorching gas giant 800 light-years away, isn't just another exoplanet. It's a cosmic jewelry box where the clouds are made of sapphires and rubies, and the winds whip them into glittering storms that would put any royal treasury to shame. This alien world orbits so close to its star that a year lasts just 2.2 Earth days, and its surface temperature soars above 2,000 degrees Celsius, hot enough to vaporize metals. But it's not the heat that makes HAT-P7b extraordinary. It's what happens in its upper atmosphere. Here, temperatures dip just enough for aluminum oxide, the same mineral that forms rubies and sapphires on Earth, to condense into microscopic crystals. These aren't the gemstones you'd find in a ring. They're tiny, swirling particles carried by supersonic winds that race across the planet at thousands of miles per hour. The first clues came from Kepler Space Telescope data. Astronomers noticed strange fluctuations in HAT-P7b's brightness, not from its star, but from the planet itself. The light pattern suggested something surreal, clouds forming on the planet's night side, then evaporating as they were blown onto the day side by blistering winds. But these weren't water clouds or even molten salt. Spectroscopy revealed the signature of corundum, the mineral family that includes sapphires and rubies. Now picture this, a twilight zone where the sky shimmers with blue and pink hues as gemstone clouds catch the starlight. Storms here don't thunder, they glitter. Winds carry these crystalline particles in vast, shifting bands, creating atmospheric patterns that change by the hour. And when the conditions are just right, the heavier particles might even rain downward, though rain hardly does it justice. Imagine a downpour of liquid gem droplets, only to be vaporized again before they reach the surface, caught in an endless cycle of creation and destruction. But here's the twist: HAT-P7b isn't alone in its extravagance. Other ultra-hot Jupiters, like WASP 121b, boast clouds of molten metal or vaporized precious stones. These planets exist in a realm of extremes where chemistry follows rules we've never seen on Earth. They force us to rethink what's possible in planetary atmospheres, challenging our notions of weather, climate, and even beauty. What makes HAT-P7b so mesmerizing isn't just its opulence, it's the reminder that the universe is a master alchemist. The same forces that create hurricanes and snowstorms on Earth can, under different conditions, craft skies of swirling gemstones. It's a dazzling example of how exotic the cosmos can be when freed from the constraints of our familiar, earthly logic. And somewhere out there, in the infinite variety of exoplanets, there might be worlds even more astonishing waiting for us to look up and wonder. Picture the universe not as a scattering of isolated galaxies, but as an intricate tapestry, threads of invisible silk stretching billions of light years, connecting celestial cities in a web so vast it makes our solar system feel smaller than a speck of dust. This is the cosmic web, the hidden architecture of reality itself, where dark matter, that mysterious, invisible substance, acts as the universe's master weaver, spinning filaments so delicate yet so strong, they dictate where galaxies will bloom like dew on a spider's silk. At its heart, the cosmic web is a relic of the Big Bang's faintest whispers. In the universe's earliest moments, tiny quantum fluctuations, random ripples in the fabric of space-time, were stretched to cosmic proportions by inflation. These ripples became the blueprint for everything. Gravity, acting over billions of years, amplified those subtle wrinkles, pulling dark matter into vast, interconnected threads. Where these filaments intersect, galaxies cluster like glittering jewels at the knots of a celestial net. The voids between them, they're not empty, just eerily sparse, cosmic deserts where matter lost the gravitational tug of war. But how do we map something invisible? Astronomers use a clever trick, light as a cosmic tracer. When distant quasars, the blazing cores of ancient galaxies, shine through the web, their light passes through clouds of hydrogen gas clinging to the dark matter filaments. Like sunlight through stained glass, the light carries fingerprints of absorption, revealing the web's structure in silhouette. Supercomputer simulations paint the rest, showing dark matter's tendrils winding through the cosmos in a fractal dance, with galaxies strung along them like beads on a string. What's truly mind-bending is the scale. A single filament can stretch for hundreds of millions of light years, yet be only a few million light years thick, a cosmic thread finer, relative to its length, than a strand of spider silk. And just like a spider's web trembles when prey strikes a strand, the cosmic web vibrates with the motion of galaxies, their gravity sending subtle waves rippling through the dark matter scaffolding. Yet the cosmic web isn't just a pretty metaphor, it's the universe's circulatory system. These filaments funnel gas into galaxies, feeding their star-forming factories. Without this dark matter highway, galaxies like our Milky Way might never have formed. Even now, the web shapes destiny. Smaller galaxies slide along filaments like droplets on a wire, destined to collide and merge with larger ones. Our local group, the Milky Way's neighborhood, sits at the intersection of several such threads, part of the Laniakea supercluster, a structure so immense it contains 100,000 galaxies, all bound by the web's invisible pull. The cosmic web forces us to rethink our place in the universe. We're not just floating in emptiness, we're embedded in a living, breathing structure, one that's still growing, still evolving. Every galaxy, every star, every atom in your body exists because of this hidden latticework, woven in the darkness long before the first light dawned. And somewhere in the depths of space, new threads are still being spun, silent, patient, and endless. Galaxies often look serene in telescope images, spirals spinning gracefully, ellipticals glowing softly, but the Tadpole galaxy tells a different story. This cosmic wreckage, floating 420 million light-years away in Draco, is a spiral galaxy caught mid-disaster, its once symmetrical arms stretched into a surreal 280,000 light-year long tail. That's not just a trail of stars, it's a scar, a testament to the violence lurking behind the universe's tranquil facade. The culprit, gravitational tides, the invisible hands that reshape galaxies like clay. Sometime in the past, the Tadpole galaxy had a close encounter with a smaller intruder, likely a compact galaxy that barreled through its disk, sending shockwaves through its structure. As the interloper passed, its gravity tugged harder on the side nearest to it, stretching the Tadpole stars and gas into an immense streamer. Picture throwing a rock into a pond, then watching the ripples freeze mid-motion, except here, the ripples are billions of stars torn from their orbits and flung into intergalactic space. What's astonishing isn't just the tail's length, it's what it reveals about galactic resilience. Embedded in that stellar ribbon are over 1,000 blue star clusters, each a nursery of young, scorching hot suns. These shouldn't exist so far from a galaxy's core, yet here they are, proof that chaos breeds creation. As the Tadpole's gas compressed during the collision, it ignited star formation in places where stars rarely form, like sparks flying from a hammer strike. The tail isn't just debris, it's a lifeline, carrying the seeds of new stellar generations into the void. But the real drama lies in the future. That tail won't last forever. Over millions of years, some of its stars will fall back toward the main galaxy, while others drift away entirely, becoming rogue stars adrift in the cosmic dark. The intruder galaxy, it's already gone, vanishing into the night after delivering its destructive blow. All that remains is the Tadpole, a snapshot of a single, catastrophic moment, a reminder that even the grandest structures in the universe are fragile, subject to forces beyond their control. Yet there's beauty in the wreckage. The Tadpole's tail glows with an eerie blue hue, a color typically reserved for the youngest, most energetic stars. It's as if the galaxy, wounded but not defeated, is defiantly painting its trauma across the cosmos. And somewhere in that chaos, there's a lesson. The universe doesn't just build, it transforms. Sometimes destruction is just another kind of creation, and even the most violent encounters can leave behind something luminous. So next time you see a serene spiral in a telescope, remember the Tadpole. Behind every placid galaxy portrait, there might be a hidden history of near misses, collisions, and tidal tales waiting to be uncovered. The cosmos doesn't stand still. It's a dance of chaos and rebirth, and the Tadpole is just one dancer in an endless ballet. Somewhere in the abyss of the Perseus galaxy cluster, a black hole is singing, not metaphorically, literally. This cosmic leviathan, weighing in at hundreds of millions of suns, has been vibrating spacetime itself, producing a sound wave so deep it's the lowest note ever detected in nature, a B-flat 57 octaves below middle C. That's a frequency 10 million billion times lower than human ears can hear, a hum so vast it could swallow entire solar systems, reverberating for hundreds of thousands of light years through the thin gas between galaxies. The discovery began as a ripple in the data. In 2003, NASA Chandra X-ray Observatory mapped the Perseus cluster's hot gas, expecting smooth gradients. Instead, it found concentric ripples, pressure waves pulsing outward from the central black hole like rings in a pond. These weren't random fluctuations. They formed a precise pattern, a standing wave with a period of 10 million years, translating to that impossible B-flat. The black hole wasn't just passively devouring matter. It was conducting an orchestra of space-time, its gravitational influence turning the entire cluster into a resonating chamber. How does a singularity sing? Imagine the black hole's accretion disk, a swirling maelstrom of superheated gas as a cosmic loudspeaker. As material spirals inward, it doesn't flow smoothly. Jets of plasma erupt from the poles, while pockets of gas collapse unevenly, creating pressure waves that propagate through the surrounding medium. But here's the twist: in most galaxies, these waves dissipate quickly. Perseus's black hole sits in an unusually dense soup of intracluster gas, allowing the sound to travel far beyond where it would normally fade. The result: A note that's been holding for 2.5 billion years longer than multicellular life has existed on Earth. Yet this isn't just a cosmic curiosity. That sound wave is doing something extraordinary. It's keeping the galaxy cluster hot. Normally, gas this dense should cool rapidly, triggering runaway star formation. But the black hole's hum acts like a simmering pot, stirring the gas gently enough to prevent catastrophic cooling while avoiding the turbulence that would shred budding stars. It's a feedback loop of staggering precision, the black hole's voice regulating the growth of the very galaxy it anchors. What makes this phenomenon so haunting isn't just the scale, it's the implication that even the most destructive forces in the universe can create order. A black hole, the ultimate symbol of chaos and oblivion, is also a maestro conducting symphonies that shape galactic evolution. And somewhere out there, in the dark between the stars, other black holes might be singing too, their voices too deep, too slow for us to hear. Yet, so next time you hear a low hum, a refrigerator, a power line, the distant roll of thunder, remember Perseus. Out there, in the silence we mistake for emptiness, the cosmos is thrumming with music we're only beginning to tune into. And the deepest notes, it turns out, come from the darkest places, at the edge of observable time, where the universe was still shaking off the afterglow of creation. Something impossible lurks. Euler's J1342 plus 0928 isn't just a quasar. It's a cosmic paradox, a supermassive black hole blazing with the brightness of 1 trillion suns when the cosmos was barely 700 million years old. That's like finding a skyscraper in the ruins of the Stone Age. According to everything we know about black hole growth, this monster shouldn't exist. Yet there it is, its light reaching us from an era so ancient. Its very existence threatens to rewrite the story of how the universe woke up. The numbers alone defy logic. Weighing in at 800 million times the mass of our Sun, this behemoth challenges every model of black hole formation. Even if it started as a massive seed, say, 100 times heftier than typical stellar black holes, it would need to gorge on matter at the theoretical maximum rate for its entire existence to reach such staggering proportions. That's like a newborn ballooning to the size of a blue whale in months. The universe simply hadn't existed long enough for conventional growth, so how did it break the rules? One radical theory points to direct collapse, black holes, primordial giants born not from dying stars, but from the direct collapse of vast clouds of pure hydrogen in the early universe. These hypothetical seeds could have formed with masses tens of thousands of times our Sun, bypassing the slow accretion process entirely. Imagine skipping the sapling stage and sprouting a full-grown redwood overnight. But even this explanation strains credibility. For Euler's J1342 plus 0928 to reach its observed size, it would have needed to feast on gas with nearly perfect efficiency, violating the Eddington limit, the point where radiation pressure should blow away the very material a black hole is trying to swallow. Then there's the environment. The early universe was a far cry from the galaxy-rich cosmos we see today. Gas was sparse, stars were rare, and yet this quasar's accretion disk burns with terrifying intensity, suggesting it found a way to tap into reservoirs of matter we can't yet explain. Some simulations suggest cosmic filaments, those dark matter tendrils threading the universe, might have funneled gas to the black hole like rivers feeding an insatiable mouth. Others propose an even wilder scenario, that the first black holes didn't grow gradually but merged in a frenzied dance, piling atop one another in the dense early cosmos. But perhaps the most unsettling possibility is that we've misjudged time itself. The quasar's redshift places it firmly in the epoch of reionization, when the first starlight burned away the cosmic fog. But what if the universe's dawn came earlier than we think? Tiny fluctuations in the cosmic microwave background hint that the first stars might have flickered to life 100 million years sooner than models predict. That slight head start could be all a black hole like Euler's J 1342 plus 0.928 needed to grow beyond our expectations. What makes this quasar so mesmerizing isn't just its size, it's the way it forces us to confront the gaps in our cosmic origin story. Every time we think we've pieced together the universe's early chapters, discoveries like this tear out the page and demand a rewrite. Whether it's new physics, unseen mechanisms of growth, or a fundamental misunderstanding of time's arrow, one thing's clear: the infant universe was far stranger, far more inventive than we ever dared to dream. And somewhere out there, other impossible quasars are waiting, their light still traveling, their secrets still locked in the dark. Most galaxies blaze with the light of billions of stars, but not Dragonfly 44. This cosmic phantom, lurking 330 million light-years away in the Coma cluster, emits just 1% of the Milky Way's starlight, yet weighs just as much. It's as if someone took an entire galaxy and erased 99% of its stars, leaving behind a ghostly outline held together by something we can't see. Welcome to the enigma of dark galaxies, shadow twins of the universe, hiding in plain sight. Discovered in 2016 by the Dragonfly Telephoto Array, a telescope specifically designed to spot ultra-faint objects. This celestial wraith defies every expectation of how galaxies should behave. At first glance, it's little more than a wispy smudge, its sparse stars scattered like dust motes in a sunbeam. But when astronomers measured its gravitational pull on surrounding objects, the truth emerged: Dragonfly 44 isn't missing mass. It's missing light. The galaxy's visible stars account for less than 1% of its total weight. The rest, a cloak of dark matter so dense, it makes this faint specter one of the most massive objects in its corner of the cosmos. So how does a galaxy end up like this? One theory paints a tragic backstory. Billions of years ago, Dragonfly 44 might have been a normal galaxy, rich with gas and young stars. But as it fell into the crowded Coma cluster, a gravitational gauntlet of larger galaxies stripped away its star-forming material, leaving behind only its ancient stellar population and the invisible dark matter scaffolding that once anchored it. Over eons, its remaining stars drifted apart, stretching into the diffuse phantom we see today. Yet against all odds, its dark matter halo survived intact, a cosmic skeleton without flesh, still holding the memory of what once was. But here's where the mystery deepens. Some dark galaxies, like the recently discovered, free-floating counterparts in other clusters, seem to lack dark matter entirely. If Dragonfly 44 is a ghost clinging to its unseen bones, these others are true anomalies, galaxies that somehow formed or evolved without the dark matter we thought was essential. It's as if the universe is running two contradictory experiments right next to each other, forcing us to question whether dark matter is the universal glue we assumed, or if there are stranger forces at play. What makes Dragonfly 44 so mesmerizing isn't just its darkness, it's what it reveals about the limits of our cosmic maps. For centuries, we've relied on light to chart the heavens. But this galaxy whispers a humbling truth. Most of the universe's structure is written in invisible ink. Every time we think we've glimpsed the full tapestry, discoveries like this remind us we're still just tracing the outlines, blind to the deeper threads weaving it all together. And somewhere in that darkness, there might be answers or questions we haven't even thought to ask. On August 17, 2017, the universe sent us a message written in ripples of space-time and a blaze of golden light. That day, gravitational wave detectors in the United States and Italy caught the faintest tremor, a vibration so small it stretched a 4-kilometer laser beam by less than 1/10,000th the width of a proton. But this whisper from the cosmos carried unimaginable weight. For the first time in history, humanity had witnessed the collision of two neutron stars, an event so cataclysmic it forged pure gold in its wake. The numbers alone stagger the mind. These two city-sized corpses of dead stars, each packing more mass than our sun, spiraled toward each other at nearly a third the speed of light. Their final embrace lasted less than a minute, their gravity distorting space itself as they drew closer. Then, in a fraction of a second, they merged, releasing energy equivalent to 1 billion suns and shaking the very fabric of reality. The gravitational waves from this event, catalogued as GW170817, raced across 130 million light-years to reach Earth, carrying with them the birth announcement of a new kind of cosmic fire, the kilonova. What makes this event so extraordinary isn't just the violence, it's the alchemy. As the neutron stars collided, their unimaginable pressure and heat ripped apart atomic nuclei, creating a supercritical soup of neutrons. In this primordial cauldron, the universe performed its most spectacular trick, rapid neutron capture, or the R process. Free neutrons slammed into atomic seeds, building heavier and heavier elements in a chain reaction that lasted mere seconds. Gold, platinum, uranium elements that take stars millions of years to forge through normal fusion were minted almost instantaneously in quantities that dwarfed entire planets. The afterglow told the story. Traditional supernova shine blue-white from radioactive nickel, but this explosion burned crimson and gold, its light curve matching predictions for heavy element decay. Spectroscopic analysis revealed the unmistakable fingerprints of lanthanide's rare earth metals flung outward in expanding shells. Within days, the fireball faded, but the legacy remained, an estimated 10,000 Earth masses of pure gold, along with other precious metals, scattered into the cosmos like glittering confetti. Here's the humbling truth: every gold ring on Earth, every platinum catalyst in a lab, even the uranium fueling some power plants, they likely owe their existence to events like GW170817. Without neutron star mergers, the periodic table would be barren beyond iron. These cosmic collisions are the universe's ultimate foundries, transforming the ashes of dead stars into the very elements that make our world and life itself possible. Yet the wonders don't stop there. The kilonova's light also solved a decades-old mystery, the origin of short gamma-ray bursts. Just 7 seconds after the gravitational waves arrived, NASA Fermi satellite detected a 2-second burst of gamma rays from the same patch of sky. This confirmed what theorists had long suspected, that merging neutron stars are the engines behind these fleeting, high-energy flashes. But the real surprise came when telescopes swiveled to the spot. Unlike typical gamma-ray bursts which fade into darkness, this one left behind a glowing ember, the kilonova's radioactive debris shining like a cosmic beacon. What makes GW170817 so transformative isn't just what we learned, it's how we learned it. This was the first event in history observed through both gravitational waves and light, ushering in the era of multi-messenger astronomy. We didn't just see or hear the universe, we experienced it with multiple senses, like a deaf person hearing music for the first time. The data matched Einstein's predictions to near perfection while offering new clues about neutron star interiors, the expansion rate of the universe, and even the nature of dark energy. So the next time you hold a piece of jewelry, remember, you're not just wearing metal, You're holding stardust forged in one of the universe's most violent acts of creation, a remnant of colliding corpses that shone brighter than a galaxy, then vanished, leaving behind the atoms that would one day become you. The cosmos doesn't just create, it recycles, and in that endless cycle of destruction and rebirth, we find our own improbable origin story. Venus is a world of extremes, a scorching, acid-drenched hellscape where lead melts on the surface and hurricane force winds whip clouds of sulfuric acid around the planet faster than the planet itself rotates. But at its south pole, something even stranger unfolds. A swirling, shape-shifting vortex with not one but two eyes locked in an endless dance. This isn't just a storm, it's an atmospheric enigma that's raged for decades, defying every rule we know about how planetary weather should behave. First spotted by the European Space Agency's Venus Express orbiter in 2006, this double-eyed tempest spans nearly 2,000 miles, spinning like a cosmic top above Venus's pole. Most hurricanes on Earth dissipate within days as they hit land or cool waters. Yet this vortex has persisted for at least 40 years, possibly far longer, feeding on nothing but Venus's runaway winds and the planet's own bizarre rotation. Unlike Earth's polar vortices, which are driven by temperature contrasts, Venus's version seems to draw energy from something far more exotic, a phenomenon called polar superrotation, where the planet's upper atmosphere races around the globe 60 times faster than the surface below. The storm's structure is even more baffling. Infrared images reveal two distinct centers of rotation, sometimes merging into a single eye before splitting apart again like celestial twins bound by an invisible thread. This isn't just chaotic, it's impossible by earthly standards. Our planet's Coriolis effect discourages such symmetrical doubling, yet on Venus the rules rewrite themselves. One theory suggests the vortex might be a standing wave in the atmosphere, a stable pattern carved by the collision of high-speed winds with the planet's slow spin. Another proposes that the dual cores are like smoke rings, linked by an unseen tunnel of circulating gas stretching deep into Venus's toxic shroud. But the real mystery isn't just its shape, it's the storm's refusal to fade. Venus has no oceans to fuel its fury, no seasons to shift its momentum. Every earthly storm relies on moisture or heat gradients to sustain itself. Yet this vortex thrives in a bone-dry, scorching environment where temperatures barely vary between day and night. Some scientists speculate that the answer lies in Venus's thick atmosphere, where the sheer weight of carbon dioxide 90 times denser than Earth's air creates a fluid dynamic unlike anything in our solar system. The vortex might be a self-sustaining engine, recycling energy through layers of sulfuric acid clouds that trap and redirect heat like a planetary-scale thermostat. What makes this tempest so mesmerizing isn't just its endurance, it's the window it offers into atmospheric extremes. If we can unravel why Venus's vortex persists, we might uncover universal secrets about how fluids behave under alien conditions, from the hurricane belts of gas giants to the plasma storms of distant stars. It's a reminder that even in our own cosmic backyard, the universe is still writing textbooks, and Venus, that broiling, acid-laden world, is holding one of the most enigmatic chapters. So while Earth storms rage and fade, Venus's polar vortex continues its endless waltz, a silent sentinel spinning in the dark. And somewhere in its hypnotic swirl, there might be clues not just about our sister planet, but about the hidden physics that govern every storm everywhere in the cosmos. They appear as faint, ghostly halos on radio telescopes, perfect circles so vast they could swallow entire galaxies. Odd radio circles, or ORC, are the universe's latest enigma, cosmic donuts glowing only in wavelengths invisible to human eyes. Discovered in 2020 by Australia's ASCAP telescope, these rings stretch up to 1 million light-years across, floating in the void with no obvious source. They're not supernova remnants, not galactic winds, not the echoes of black hole jets. They're something entirely new, and astronomers are scrambling to decode their origins. The first clue to their strangeness: ORCs don't match anything in the known cosmic playbook. Most radio emissions come from high-energy events, exploding stars, colliding black holes, or the frenzied particle jets of active galaxies. But these circles are eerily symmetrical, their edges crisp as if drawn with a compass. Even more baffling, they're almost entirely empty at their centers. No visible galaxy, no star cluster, no telltale flicker of a black hole's accretion disk. It's as if someone took a celestial cookie cutter and stamped these rings into the fabric of space itself. One leading theory points to shockwaves from a cataclysmic event, perhaps a gargantuan stellar explosion, a so-called starburst so violent it sent ripples through intergalactic gas like a stone dropped in a pond. But there's a problem. ORCs are too big, too clean. A supernova's blast would fray at the edges, its energy dissipating unevenly. These rings are pristine, their structure too perfect for chaos. Another idea suggests they are the aftermath of a black hole's feeding frenzy, where jets of plasma punch through galactic gas, leaving behind expanding bubbles. Yet no known black hole produces rings this colossal or this symmetrical. Then there's the wild card. Could ORCs be the imprint of something even more exotic? Some theorists whisper about dark matter annihilation, where hypothetical particles collide and release bursts of energy. Others propose they're the fingerprints of cosmic strings, defects in space-time left over from the Big Bang, vibrating like guitar strings and ringing the universe with radio waves. The most tantalizing and unsettling possibility: they might be the remnants of a phenomenon we've never witnessed before, a celestial process so rare we're only now seeing its echoes. What makes these radio circles so mesmerizing isn't just their mystery, it's the way they force us to admit how much we still don't know. For every cosmic rule we've written, the universe seems to keep a secret in its back pocket, waiting to surprise us. ORCs could be relics of an ancient event or heralds of a new physics. Either way, they're a reminder: the more we map the skies, the more we realize how much uncharted territory remains. And somewhere in those faint radio whispers, there might be clues to a chapter of the cosmos we haven't even imagined yet. Stars are supposed to follow recipes-specific mixtures of hydrogen, helium, and trace heavy elements that dictate how they form, burn, and die. But SDSS-J 102,915 plus 172,927 isn't just an oddball. It's a cosmic impossibility. This ancient star, flickering in the constellation Leo, is over 13 billion years old, one of the oldest objects ever discovered. And yet it's missing the one ingredient every star of its age should have: metals. Not just low on them, nearly devoid. To understand why this is so baffling, picture the early universe as a kitchen stocked with only the barest essentials. After the Big Bang, the cosmos contained almost nothing but hydrogen, helium, and a pinch of lithium. The simplest ingredients, the first stars, called Population 3, were born from this pristine soup, their nuclear furnaces fusing these light elements into heavier ones like carbon and oxygen. When those pioneers exploded as supernova, they littered space with metals, seeding future generations of stars with richer chemistry. By the time our sun formed, it inherited a well-stocked pantry. About 1.4% of its mass is metals. But SDSS-J 102,915 plus 172,927 It clocks in at less than 1/20 millionth the Sun's metal content. That's like finding a 5-star restaurant serving nothing but saltine crackers. Theories scramble to explain how this relic survived unscathed. One possibility is that it formed in an isolated pocket of the early universe, a rare bubble untouched by the pollution of those first supernovae. Another suggests it might be a surviving fragment of a much larger star that somehow avoided contaminating itself, like a chef who never tastes their own cooking. But the most radical idea, that our models of early star formation are missing a key step, a process that allowed some stars to condense from nearly pure hydrogen without the usual metal catalysts. What makes this star so mesmerizing isn't just its defiance, it's the time capsule it represents. Its light carries the chemistry of a universe still in its infancy, before galaxies finished forming, before planets were possible. Studying it is like reading a scroll thought lost to time, one that might rewrite the opening chapters of cosmic history. And somewhere out there, other primordial relics might still glow in the dark, waiting to tell us how little we truly know about the universe's first dawn. Imagine watching a supernova explode twice, first in 2014, then again in 2015. Not a new explosion, but the same event, replaying years apart like a glitch in the universe. That's the eerie magic of the time-delayed quasar, a cosmic illusion so precise it bends not just light, but time itself. At the heart of this phenomenon is Einstein's old prediction. Gravity doesn't just pull, it warps the fabric of space, creating natural lenses that distort and multiply light from distant objects. But the quasar known as SDSS J1004+4112 takes this to another level. Its light, traveling toward us for nearly 7 billion years, passes through a massive galaxy cluster along the way. The cluster's gravity splits the quasar's image into two, not just side by side, but staggered. One path is slightly longer, forcing the light to traverse more space-time, making it arrive years behind its twin. The result, a celestial echo, the same cataclysmic flare from a supermassive black hole's outburst, playing out twice in our telescopes like a cosmic director's cut. What makes this double vision so valuable isn't just the spectacle, it's the science. By comparing the two images, astronomers can measure the universe's expansion rate with unprecedented precision. The delay between the quasar's twin appearances acts like a calibration mark, revealing how much space stretched during the light's journey. But there's a catch. The galaxy cluster doing the lensing isn't just a static lens. It's a dynamic, messy place, its dark matter distribution clumpy and uneven. That means the delay isn't constant. Tiny fluctuations in the cluster's mass can add microsecond variations to the quasar's replay, offering clues about dark matter's elusive nature. Then there's the quasar itself, a beast. The original source is a supermassive black hole devouring matter so furiously, its accretion disk outshines its host galaxy. As gas spirals inward, it heats to millions of degrees, blasting radiation across the cosmos. But here's the twist: the lensed images don't just show the same outburst at different times. They capture it from slightly different angles, like a hologram revealing hidden facets when tilted. One image might magnify a flare from the disk's edge, while the other highlights jets erupting from the poles. It's as if the universe handed us a 3D model of a black hole's feeding frenzy, with time lapse included. Yet the most tantalizing possibility lies in the future. If we catch a quasar in the act of flickering, say, a star being torn apart by tidal forces, we could witness the same event twice, first in the early image, then years later in that late one. It's the ultimate spoiler-free time machine, a chance to study cosmic violence with advance notice. Astronomers are already scouring the skies for such pairs, hoping to catch a supernova's death throes or a black hole's outburst in delayed stereo. What makes the time-delayed quasar so mesmerizing isn't just the illusion, it's the intimacy. For once, we're not just observers of the distant cosmos, we're participants in its chronology, watching the universe edit its own highlights reel. And somewhere out there, other gravitational lenses are surely bending light in ways we haven't yet imagined, hiding echoes of the past or previews of the future in plain sight. From the silent pull of dark matter to the glittering storms of distant diamond planets, we've journeyed through 40 cosmic wonders that defy imagination. Each one is a testament to the universe's boundless creativity, a place where black holes sing in B-flat, where galaxies stretch into perfect rings, and where time itself can bend to replay a supernova like a cosmic encore. These aren't just curiosities, they're clues to a reality far stranger than we ever dreamed. But here's the humbling truth: for every mystery we've solved, a dozen more emerge. The Great Attractor tugs at galaxies with unseen hands. Fast radio bursts flicker like Morse code from civilizations we may never understand. Rogue planets drift through the void, perhaps carrying life in their hidden oceans. The cosmos doesn't just challenge our knowledge, it flips the board and rewrites the rules mid-game, and that's what makes it exhilarating. The real magic isn't just in the wonders themselves, but in the human instinct to chase them. Centuries ago, Galileo pointed his telescope skyward and shattered the illusion of a perfect celestial sphere. Today, we train infrared eyes on galactic ghosts and listen for gravitational whispers from colliding stars. Our tools evolve, but the question remains the same. What's out there? That relentless curiosity, the refusal to accept we don't know as a final answer, is our greatest superpower. So as this journey ends, remember, the universe isn't a static backdrop. It's a living, breathing story, and we're just turning the pages. Maybe you're drawn to the haunting beauty of the pillars of creation, or the chilling silence of the Fermi Paradox. Perhaps the rogue black hole trailing stars like breadcrumbs fuels your imagination. Whatever it is, that wonder is your invitation to keep exploring. The next cosmic revelation could be a telescope click away, hidden in data we've yet to decode, or written in light that's still traveling toward us. The cosmos isn't done surprising us, neither should we be done searching. So tell me, which of these 40 wonders left you starstruck? Drop your favorite in the comments, and let's keep the conversation as infinite as the universe itself. After all, the night sky isn't just a sight to behold. It's a call to adventure, and the next chapter, it's yours.